Okay, a very good morning to all of you, my dear participants. Today is the third lecture in this series, titled as Evolution of Protostars. In the last two lectures, I have described the giant molecular clouds and what are the conditions under which the collapse occurs and forms the clumps and cores out of which the protostars finally evolve. Now, during their evolution, the protostars manifest a number of features through which an astronomer understands that, yes, these are the stars in formation. Both low mass stars as well as high mass stars show such manifestations, and we need to detect that. Mind you, the high mass star formation regions are very far off. The nearest massive star formation region, like for instance the Orion, is more than 450 parsec, several hundreds of about 500 or more light years. So these are very far off. Also, these massive stars are embedded in dust and gas and undergo a large extinction, which I have explained. Now, the extinction in the visible in these regions can reach even 100, 200 like that. So even in the near infrared, the extinction is quite large, 10 or 20. So these are extremely difficult to observe compared to the low mass stars. So you should not understand the high mass star as just the scale up version of low mass stars. Now in this lecture, as I said, evolution of protostars, some observational inputs and of both low and high mass stars, structures, jets and disks in these stars, in these protostars, through which actually they manifest themselves. Now this is a low mass star clump taken in 1.3 millimeter region, okay, very long wavelength region. And this is just a clump, it is forming. Now, the astronomers have observed a number of such clumps and found out the mass function of these clumps, which is m raised to -6, -0.6 plus or -0.3. So you see the large error bar here. So a lot more observations are required. As someone was asking, is there anything else to do in this? There's a lot of things to do. Theoretically, we may understand a lot of processes, but observationally, we need to do a lot to come and explain the formation of low mass stars vis-a-vis the high mass stars. Now, such clumps actually, they exhibit very nice blackbody type of curves, spectral energy curves. This is a wavelength versus the flux density. So you can see, you can fit actually very nice blackbody equation, Planck's equation, Planck's distribution for a temperature of T equal to 30 degrees Kelvin for an object called IRAS so and so. So these are all protostellar cores. And one more such protostellar core, which is now colder actually, 13 degrees Kelvin, that is also nicely fitting. So such pre-stellar cores need to be observed and find out the mass function. And we know the mass function of the stars fairly well, which are already in the main sequence, and compare these mass functions with the pre-stellar cores and so on. Now, the full slide is not coming up nicely, but anyway, I'll move it up and down. The core nuclear energy in a pre-main sequence star or a protostar is not yet created. because the cores have not yet reached the temperatures required for the onset of the nuclear reactions. So mainly the energy that the star sustains, or the pre-stellar object has, is the gravitational energy, because as it contracts, it heats up. So that heat energy is the one which is sustaining. Okay. So if you were to take a solar mass object and only the heat energy, because of the contraction, has to sustain it, you know, through the Kelvin-Helmholtz time scale, that it can only last for about a few times 10 to the power of 7 years. But we know from the dating and all these isotopic techniques that sun is much longer. Therefore, the nuclear energy has to be put at the core in order to make these stars live their long lives, because we know that the stars long very lot of billions of years, but the sun, for instance, 10 billion years. So 10 to the power of 7 is very small number. So heat energy cannot sustain that. So anyway, the point that I am trying to make here, that the L internal, the luminosity internal, is less than the luminosity outside, because the outer regions actually lose the energy most than the inner regions. At the core, actually at the center of the core, nothing is lost, but as it goes out to through the radial distance, the surface actually loses much more energy. Therefore, the L star, if we call the surface luminosity, that is more than the internal luminosity. Whereas if you actually reach a star in which the nuclear energy is now available, because the temperatures have risen to 10 to the power of 7 degrees and so on, then there is an equilibrium, and therefore the luminosity now goes as L star is equal to 4 pi r star square. In this also the same formula, but here we have reached an equilibrium. Here in this case, the temperature luminosity is ever changing with time. Here it is not so, it now has reached equilibrium and therefore it's constant. So in this situation, the L internal is same as the L star on the surface. So that is the difference. Now if you look at the internal structure of a protostar, here what I have depicted here, this is a protostar core. In this core actually, the temperature is sufficient about 1,000,000 degrees Kelvin, at which the deuterium reactions can start. That means a proton and a proton will combine to give a deuterium nucleus, and the deuterium nucleus in turn takes on another proton to form 3 helium isotope. Okay. Now the next reaction actually, that 3 helium plus 3 helium, that will go to the 4 helium plus 2 protons. But the temperature is not sufficient to reach that particular last stage. It just stops at the deuterium level. Okay. So that is the deuterium bonding here. Now this is now generating a radiative precursor, because now this is quite hot and therefore the radiation is now emanating from this region, this surface, and matter also is accreting onto this one, because star has not finished the formation yet. It is still in the formation. Accretion is still going on. Therefore, there will be an accretion shock which goes outside like that and then tries to evaporate whatever is material is available in this region. So there will be a shock propagating outwards, and that will evaporate the dust and so on surrounding that. So this is the dust destruction front over here, and this is the dust envelope itself, and outside which there is an outer envelope in which gas and so on. So this is actually, this surface of the dust envelope is called the dust photosphere. But now you see that there is an opacity gap. There is almost no material at all here. Therefore, the opacity, that is the cross section for photon absorption by the stellar material, is almost not there. It's 0. But as you go into the dust envelope, basically the radiation is absorbed by this dust envelope. And radiation also tries to evaporate and destroy the dust. And finally, of course, the star should come out. But by the time the accretion is still going on. So this is the internal structure when the deuterium burning is going on. Now, stars, we believe, blackbody radiation, you all perhaps studied in your graduate and postgraduate studies. Stars radiate like black bodies while on the main sequence phase. Okay, also in the pre-stellar course, we have shown that they are very cold bodies radiating as black bodies. So basically, this is the equation for Planck function. S lambda is equal to so and so. And the peak value, peak lambda, that means this curve peaks at a particular lambda or frequency depending upon the temperature. And lambda peak times the temperature is this much, 2.898 times a million, 10 to the minus 3 millikelvin. Okay, that's the formula. So you will know, given a temperature of the star, what is the peak wavelength. For instance, the sun, you know, it occurs at the yellow region and so on. So for these stars which are very low temperatures, the peak occurs in the near infrared and far infrared and so on, millimeter and so on, for the protostellar objects. Now this is called the Hertzsprung-Russell diagram, named after the two astronomers, astrophysicists, who actually first put this diagram together, Hertzsprung and Russell. In this diagram, it's plotted. The effective temperature of the star is plotted, which is decreasing from the left to the right. So 30,000 degrees Kelvin to 3,000 and so on degrees Kelvin. So hot stars and cold stars. Now sun is here, okay, at this temperature, around 6,000, let's say. The luminosity, which is normalized to sun, okay, 1 luminosity, solar luminosity. And this is the absolute magnitude, which we have defined already. What are these quantities? The massive stars are over here, low mass stars are over here in the below. So this is called the main sequence. What is the significance of the main sequence? Significance of the main sequence is that when the star reaches this sequence, the hydrogen burning is now started actually. So then you call it a star. Okay. So hydrogen burning has to start in the course. So the helium is being produced by nuclear reactions at the core. That is the longest phase in the life of a star. This you all know. Now, astronomers, what they do is they make observations of these protostar objects, protostellar objects. Okay, they try to estimate their luminosities, they try to estimate their temperature, surface temperatures, and try to put them on this diagram. With time, these are mostly calculations, okay, but in a cluster you can also find out which phase such protostars are. So they made calculations or computations and found out what are the tracks that they take from the birth line to the main sequence. So these are actually first calculated by the Japanese astrophysicist Hayashi, and then there onwards there are several additions, subtractions made, so it has been fine-tuned. Now this is one such diagram, in which again this is Hertzsprung-Russell diagram sort of a thing. So here you can see the zero age main sequence. That means the star has just reached this point, a 3 solar mass star has just reached. Therefore, this is called the zero age main sequence for the star that has a mass of 3 solar masses. So like that. So here is plotted 0.1 solar masses to about 6 solar masses and a little more. And what are these lines? Let us see. Now this is the isochrone. That means if you have a cluster, these cluster stars which have different masses, how they evolve at 1 into 10 to the power of 5 years after their just contraction has started. So this is that line here. So similarly, after 1 million years, this is the line. After 10 million years, this is the line. After 100 million years, this is the line. Almost coincides with this 0-age mean sequence stars, because most of the stars do reach by that time the main sequence. And 0.1 solar masses is basically the limit for nuclear reactions. We have said that the hydrogen nuclear reactions, 0.08 solar masses. Below that, the temperatures don't go to 10 to the power of 7 and so on degrees Kelvin, and therefore they cannot start the hydrogen nuclear reactions. But however, below this 0.08 solar masses, for some time, the deuterium burning can take place, which I have briefly mentioned. Deuterium, because this has the hydrogen burning has some stages. Okay, so it is only going up to certain stage, but not beyond, because you require higher temperatures to go complete the cycle. So these stars are unable to do that, and therefore they are failed stars. They could not become stars. Basically, white dwarfs, there is a question, white dwarfs, what are the white dwarfs, sort of a question. Okay, so basically white dwarfs are evolving from these low mass or intermediate mass stars below about 9 solar masses, including the sun, will go to white dwarf stage. So they will go to the giant stage. There will be a heavy mass loss, and they will go to the planetary nebula. So all the envelopes, outer envelopes, go into the interstellar medium and show themselves as, manifest themselves as planetary nebulae, and the core itself, which is about 0.8 to 1 solar mass, 0.8 solar mass typically, that will evolve. It will go all the way like that. Temperature increases, surface temperature increases at the same luminosity, and then cools down. So all the white dwarfs that you see here below, they're all almost dead. Okay, so it's very difficult to find them because of low luminosity. As you can see, 10 to the minus 2 times the sun, and even below. Okay, so these are the evolved stars, the course of which going into these white dwarfs. Evolution of low mass or intermediate mass stars below 9 solar masses. That will give you the white dwarfs. So that is a stellar evolution. So this I have explained. So high mass protostars are not optically visible as some of these low mass protostars are, and they appear suddenly in the main sequence itself because the accretion is still going on while these stars are on the main sequence. They have reached the main sequence. That's the difference, which I have said yesterday or Friday. Now these are actually what they have done. The observers, astronomers, they have taken the Orion Nebula cluster, and they have taken about 705 protostars or pre-main sequence stars, and they have plotted on this one, the isochrone diagram. This is a HR diagram on which isochrones are plotted. That means after the contractions birth line, start of the birth line, if you go for 1 million years, 10 million years, and so on, where do they fall? So you can see a large number of low mass stars are here, and as you go, the number is decreasing as you go towards higher masses. Okay, so that's how the mass function also tells you that. All right. So this is how one can understand these stars are in pre-main sequence stage, and these stars are in main sequence stage when you make an observation on the sky. Now this is another diagram in which I have actually shown from 0.8 solar masses to up to about 60 solar masses. Now high mass stars to some extent are included in this one. Now this squares over here are the onset of the time at which the onset of deuterium burning takes place. Deuterium burning in the core. Okay, this deuterium burning, because the deuterium itself is a very small in number, it is not a most abundant isotope of hydrogen, therefore it's a low abundancy. Because of its low abundance, it's a slow process. It takes time. Okay, and therefore the luminosities decrease here for a number of stars here. You can see that the luminosity is falling off here. Now this is a track wherein the radiative envelopes are developed here. So in the low mass stars, actually the radiative envelopes are not at all there. Okay, this is a convective core. The cores are convective for a number of stars here, but as you come down to the low mass stars, mostly it is convective. Okay, like that. So basically there are stars below about 0.3 solar masses or so that are purely convective while they are on the main sequence. There are massive stars in which they have sun-like stars or low mass stars or intermediate mass stars in which they have radiative cores but convective envelopes, and you have high mass stars in which convective cores and radiative envelopes. So this is basically leading you to that sort of things. These are all called Hayashi tracks, pre-main sequence evolutionary tracks. These are okay. Now this is the evolutionary stages of low mass protostars. Now we'll talk something about the low mass stars and then go to the high mass stars. This is a spectral energy distribution in which the spectral energy is plotted against lambda. This is the energy lambda, F lambda flux here against the lambda. So you can see in the very beginning stage, when the star is still accreting matter, I have shown you one example also, the core of such a protostar. It is emitting like a black body, all right, but it's a very cold black body, a few degrees Kelvin or so, a bit about 10-20 degrees Kelvin or so. The accretion is going on still. So this age is about 10 to the power of 4 years. Okay, this is the main accretion phase for a low mass star. Now then comes what is known as, this is a class 0 object for the low mass stars. Then you get to class 1 objects, wherein now the accretion is now coming to an end slowly, but still it is accreting. But then the spectral energy distribution has taken this kind of a shape. The solid curve over here, I hope you can see. This is a solid curve. Okay, but if it were to be a black body, this is the black body. That means above this black body, that means you have a surface, nice round surface, but surrounding that you have dust and other material. So this portion is the excess infrared. This is occurring in the infrared region. So this is the excess infrared emission. So this excess infrared emission is occurring for these stars because of this presence of this envelope. So envelopes get heated from the radiation coming from the core here, right, stellar core, and then that is re-emitted. The dust particles absorb this radiation in optical and ultraviolet, they get heated up, they re-emit it in the longer wavelength infrared. Okay, that's what is happening here. That is why you are getting extra radiation because of this envelope. Now come to the class 2 type. Now slowly the accretion is now coming to an end. There is a disk still left here. Okay, it is now the spectral energy distribution itself is now coming down. This is the black body, and this is the excess radiation due to the dust. Excess radiation due to the dust is now coming down, as you can see, as the star is now evolving into a main sequence or a 0-age main sequence star. Now finally, in the class 3 stars, almost the disk has disappeared almost. So you have the stellar black body coming. It's a low mass star, peaking around 2500 or 2300 degrees Kelvin here. Okay, M-type star. Now, so this took about 10 to the power of 7 years to come from there to here, up to here. Okay. Now, what you can do is that you take such pre-stellar objects, pre-main sequence objects, and observe it in several wavelength bands, and construct yourself such distribution, and find out what is the excess and find out what is the actual surface temperature of the core, and then you will know what is happening, what is the class of that object. Now, during this stage, class 2 and class 1, these are called debris disks in the parlance of the astronomers. These are called the debris disks. And planets, they have to form from the material that is going around this star at this stage, class 2 and class 1 stage. So these are the accretion disks here, debris disks here, as I've shown, in the side on and face on, edge on and face on. Okay. So planets have to form from this material. This actual star is at the center somewhere here. Okay. Planets have to form from this material. That's it. We'll come to that in I think day after tomorrow. Now, the evolutionary stages of low mass protostars we have just now talked about. So we have because most of these low mass stars are discovered in Taurus Auriga region, where you have large number of low mass pre-main sequence stars. They are called T Tauri stars because T Tauri is the first member discovered in that Taurus Auriga region. So that's called T Tauri. So all those stars which resemble this T Tauri are all called T Tauri stars. That's how we astronomers nomenclature goes. So there are classical T Tauri stars, class 2 and class 1. There are weak T Tauri stars, which is class 3. And you understand by now that why we are calling it weak class 3, weak T Tauri star, because the circumstellar material here is almost not there, but it's still there. That's it's weak compared to the earlier stage. Now the accretion rates at the class 0 stage is 10 to the minus 4 solar masses per year, quite large accretion. And when you come to class 1, accretion rate decreases 10 to the minus 6 solar masses per year. Now accretion during protostellar stage determines the final mass of the star, because almost 10-20% of the mass is accreted during this stage. So the final mass is finally decided by the accretion rate and so on. Now these are actual observations of such stars, some of such stars. This is a wavelength here again, spectral energy. This is spectral flux, lambda f lambda. This is some units, Fs per centimeter square per second. This is lambda in micrometer, okay, log lambda. So if you look at this object, WL12, this is class 1. Here also you can see the earlier graph, okay. They're almost flat. Okay. So that is same thing is depicted here, actual observations. These are actual observations. So this is flat. Why? Because of the excess radiation coming from the envelope, the infrared envelope. This is class 2. You can see that is just coming down. And if you look at the class 3 object, it's almost like a black body of 2000 degrees Kelvin. Okay, these are actual observations. All these dots are actual observations at various wavelengths, visible to infrared. Now there is an index for this determined. Alpha IR is d log lambda f lambda by d log lambda. So if the d log this alpha IR is positive, then these are class 1 stars. If it's almost positive, if the index reduces, then it's class 2, and if it is negative, then you know that it has reached the class 3 and probably the 0 age main sequence. That's how I understand from these observations. Now the protostars, the low mass protostars, they also manifest a number of very beautiful structures like jets and outflows. okay, such as this. The Hubble Space Telescope has picturized these jets here in the visible light. You can see this. There's another example here, and here you don't see that because of the presence of dust cloud, which is absorbing, which is offering an extinction to the visible radiation. So this has to be observed in the infrared. Now one more example here, multi-wavelength observations. It's a bipolar jets in the low mass protostar. You can see this is the somewhere here within this is a protostar core, and all these contours, white contours, are carbon monoxide 1.3 millimeter observations. This is a mapping. Okay, so this jet is mapped in carbon monoxide. And these pink structures here, all this, okay, these are molecular hydrogen 2.12 micrometer line in the near infrared. They are here. Okay. Now these contours, red contours in the center, they represent the dust emission, continuum emission from the dust. Okay, in the infrared again. And this much is about 5,000 astronomical units. Astronomical unit, 1 astronomical unit is the average distance between the Earth and the Sun. Okay. Now the same object in two velocity regions. In this, I have shown this. So this is the molecular hydrogen. These are the contours of the carbon monoxide. This is the dust core. The same thing here, but this is shown in the low velocities. Velocities below about 8 kilometers per second. They are here. And more than 80 kilometers per second, reaching up to 100 kilometers or so, are shown here. Okay, so the velocity as you go from the center of the jet outward like that, it is decreasing. Also, velocity is increasing as you go towards the outer region. So it is getting accelerated as you go outwards. So these are also collimated, as you can see. Very highly collimated beam kind of a thing, collimated about 10 degrees. Velocities are reaching about 100 to 200 kilometers per second. And these are accelerated jets, some of these. And velocity increases with the luminosity of the central object. Okay, the central object, that is the core, the protostar, is high luminous. Then the jets are higher velocity. There are also observed the asymmetric jets. Asymmetric jets, that means this jet is truncated with respect to this jet. You see only a small portion of this and a longer portion of this one. So they are asymmetric. The reason could be that there is the other outside material in the interstellar medium that could be very dense over here compared to this one. Therefore, it is offering a resistance for this jet to propagate. So that could be one reason. And these jets are also variable with time. Now, some more examples. For instance, here we are observing in two emission lines. One is the hydrogen alpha at 6563 angstroms, which is shown in the blue here, and this red region, faint red region here, is the sulfur, singly ionized sulfur. Okay, this is also in the visible wavelengths. Okay, and 6717 angstroms, and this is the star from which these are emanating, these are produced. This is the protostar. There are also such shock-like appearance. So again, here green is hydrogen line, and the pink traces are sulfur line, singly ionized sulfur line. And this astronomers could not find the origin of this one. So there are several such objects where they could not actually project it onto a protostar, because the field is very crowded with so many protostars. So we don't know which one is actually emitting this one. So that problem also arises sometimes. Now, why this is happening? Why these jets and outflows are happening? So basically, there is a model proposed by Xu et al. Some time back, that you have a star here, protostar here, okay, with a radius r star, and it has a magnetic field. So this is a magnetic field based explanation. So star has a magnetic field. As it contracts, it has a magnetic field. Okay, a few hundred Gauss or so. Now these are the magnetic field lines. So normally magnetic field lines go like that, like that. So this is a mirror image. The downwards also you can imagine. So this is the line here. You can imagine the other half as a mirror image here. Okay. So these magnetic field lines are going like that, like that, like that, like that, like that. Now there is an accretion disk here because it's a protostar. So this is the accretion disk. Now this accretion disk cannot just push the magnetic field lines all the way down to this, especially when the magnetic field is quite strong. Therefore, it stops at some distance, which is called Rx. Okay, here. So this is the accretion disk all the way here. This is a star. These are the magnetic field lines. Now, what happens is the magnetic field lines get pinched. They become like that. They become like that at this point. At this point, they become like that. Okay, and the material from the disk here, they flow what is known as funnel flow onto the star. So wherever the flow goes and touches the surface of the star, so energy is generated there because it's shock there, and ultraviolet hotspots they're called. Here ultraviolet radiation is generated. Now the other field lines here that is shown here, they are going like that. Okay, here also on the downwards also they go like that. Now they carry the material because the escape velocity outside these regions are much larger or much smaller compared to the Albanic velocities, the characteristic velocity in a magnetic field, plasma in a magnetic field called the Alfvén speed. Therefore, this matter can be escape into the interstellar medium. So this is called the X wind. Wind, when you say, when the star is losing the matter, then you say star is having the wind. Okay, the wind can occur from the star, from the disk also. So wind is a mass loss basically. Now accretion is the mass is now gained from the disk. The matter is being accreted. So matter is getting accreted here as well as matter is being lost here. So both are happening here. And at the polar regions, through the magnetic field lines, the jets are occurring. Now the collimation of these jets can be controlled by how close that the disk can come to the star. So collimation is explained. The production of the X-rays here, because this region, Rx region, is getting heated up. Okay, I'll show in the next diagram. So X-rays are emitted here because X-rays are found in low mass stars, low mass protostars. Single jet emission is not there. As I said, there can be a symmetric jet, but by symmetry, because the magnetic field lines are going like this, right? North pole, south pole, right? So single jet is not expected unless the other side jet, that is truncated by the high density interstellar matter. So it can get truncated but not completely removed. This basically explains two jets, symmetric on both sides through the polar regions. So what is happening is that the same thing is seen here. Okay, the equatorial plane. So this is a star. This is the Rx, radius Rx. These are the field lines. So as this is the co-rotation. The co-rotation ends here. So after this distance, co-rotation ends. Below this, co-rotation. After this, there is a Keplerian motion. Therefore, there is a differential motion here, and therefore the field lines are twisted here, and they offer a torque on the reverse direction that will actually take away the angular momentum, and then this region gets heated because energy cannot be lost like that. It has to appear in some other form. So the heating occurs here at the Rx region. That leads to X-rays. Now there are shocks which are happening, which I have said already. There are accretion shocks and so on. So simply putting, this is the column density here, okay, and this is the precursor here. When the shock is propagating into the medium, the temperature rises, because it's compressing, and also the density rises here. And at the shock interface, after the shock, the temperature slowly comes down. Now, in the wake of the shock, I'll quickly go through this. In the wake of this shock, so as the temperature is rising, okay, the plasma is heated up, and that heated gas actually emits a lot of radiation, and that thermal energy actually excites and ionizes a lot of species. That's what is shown here. So if you have the shock velocity v square, so the kinetic energy half mv square is thermal energy 3/2 kT. So the temperature here that it can give rise is proportional to the v square, shock velocity square. So here is plotted shock velocity in kilometers per second, 10, 100 and 1000 here, and this is a degree of excitation. So the carbon monoxide in the low shock velocities here, below 10 kilometers per second also, this carbon monoxide millimeter lines, the rotational lines can be excited. And a little hotter shocks, you have the rotational lines of molecular hydrogen, rotational vibration lines of molecular hydrogen in the near infrared as the temperature is now increasing and the shock velocity is increasing. These atomic oxygen lines can be seen, that is excited. Now the oxygen, nitrogen, sulfur are ionized here, singly ionized. So those ions will emit their characteristic radiation. H alpha is here. Now doubly ionized oxygen, the famous green line 5007 angstrom line gets emitted if the shock velocities are more than about 100 kilometers per second. So it depends on the ionization potential of this, how many electron volts it requires to remove an electron. And at much higher velocities, silicon 4, three electrons are removed from the silicon, carbon 4, oxygen 6, and so on, they occur. And also thermal X-rays also can be emitted from these shocked regions if the shock velocity is sufficiently large. Now this, so when one observed the emission spectra using a spectrograph of the T2 stars, one saw actually a number of emission lines here. These are the object names here. They are all in the Taurus region, Taurus Auriga region. And you can see the H alpha line, H beta line, and all the hydrogen bomber series. You can see this is a visible wavelength from 4000 to 6000 angstroms. Apart from that, there are other lines also can be seen. Okay, now massive protostars, when you talk about, there basically there is a large difference between the low mass protostars and the high mass protostars. Free fall time scales, which I have already said, are much larger compared to the contraction time scales here for the high mass stars. So they reach the main sequence before the accretion starts. That's the fundamental difference between the low mass star and high mass stars. Massive stars, they also are capable of exhibiting jets and outflows. They do actually exhibit jets and outflows. So these manifestations are seen commonly in all them, but these manifestations like jets and outflows are more energetic in the case of high mass protostars, and the mechanism itself could be very different. In the low mass manifestations, jets and outflows, we had taken the resort to the magnetic field interference. In this, you don't need a magnetic field. That's what we will see here. These are very difficult to observe, as I have already said. Large extinction is there because of dust and gas around that. Now, this question we have already understood. Let me repeat that again. The formation of high mass stars, is it by accretion or coalescence? Because for the accretion process, there is a condition above the 8 to 10 solar masses. The condition should be that gravitational energy should be more than the radiational radiation pressure energy. But that requires actually a large, a high rate of accretion onto the star to overcome the gravity. And coalescence is another process that is suggested. That means if you have stellar density in a very dense cluster of stars, it is 10 to the power of 6 to 10 to the power of 8 stars per parsec cubed in that volume, then the stars can dynamically affect each other, coalesce with each other, and two intermediate mass stars can coalesce to form a large star. That is possible. But recent studies have actually shown that accreting through a disk also is possible in the high mass stars. Not you don't have to go for a coalescence, but that doesn't rule out the coalescence as an alternative mechanism. Okay, so that's what we are now going to see. Now, accretion and mass loss in massive protostars. When you say accretion, accretion is basically matter is given to the star by the disk or the outer regions, like a disk here and a cloud core also is here. Okay, so it is not the matter that is actually falling onto the star, but matter is lost from the disk. That is the accretion rate at which the matter is given out from the disk to the star, because all the matter cannot or may not fall on the star and contribute to its mass finally. Some of it may get lost also. Okay, so the cloud core contributes the mass into the disk. So this is a star here, massive protostar. You have a disk here created by this accretion from the cloud core. You have a disk now. So the cloud core is pumping matter into the disk. Now disk is pumping matter into this at a rate of m dot s accretion. So this is star accretion. This matter is accreted by the star. Star is also losing mass through this wind here. Disk also is losing mass through the disk wind here. So the total from the system itself, the entire system itself, the total mass loss is just not the mass lost from the star, but also from the disk. These two put together will form the mass lost from the entire system. So similarly, accretion from this disk as well as from the cloud core, that forms the final accreted mass onto the star. Now cloud core can also contribute to the jets and outflows through this channel. So this is a very complex process basically for the high mass stars. Now this is a view graph in which accretion is now, as I have said, coming from the disk here. This is the disk here. This is the disk here coming onto the star. Okay. Now, because of these accretion shocks which I have mentioned earlier, the matter can get heated up to very large values, and it contributes to very hard radiation. And that hard radiation, ultraviolet and so on, that radiation actually ionizes and excites these regions here in the disk. So the outer regions of the disk therefore are now ionized. So we have an ionized disk here, the H2 disk, ionized hydrogen disk here. Now the ionized hydrogen disk has an interface here with the dust particles around this region. So ionized hydrogen region, neutral hydrogen region, molecular hydrogen region. So these are all now the matter is going into the star, being accreted by the star through this channel. Right? Now the dust here, present here in the interface, that will slightly absorb this radiation and stop the further evaporation of the gas. That's how the H2 molecular hydrogen survives behind the dust particles. Now this is where the escape velocity, this is a radial distance above which the escape velocity is less than the typical sound velocity. Yeah. So matter can escape. Okay. through these regions. Inside this region, the escape velocity is more than the sound velocity, so they cannot escape from this region, in this region. Now, this is a cavity here above the disk, which is having a wind here. Okay, so slowly the mass is lost through these regions also. That forms the jet here. Now, the collimation of this jet here is controlled by the how strong the stellar wind is, okay, or how weak the ionizing photon flux from this disk. Because all this matter is ionized by the radiation coming from this disk. So how weak it is and how strong the stellar wind is, that determines the collimation. That will give you a lesser collimation. So it will be fanned out like that, as is shown here. But if these are strong, okay, if this is let us say is a weak stellar wind and a strong ionizing photon flux, then you have a more collimated outflow. So we have produced here an outflow scenario without the magnetic field. It doesn't mean that the magnetic field is not present in these things, but you don't need magnetic field to produce this scenario. Just by this magnetohydrodynamics, normal hydrodynamics itself, you have produced this. So this is by Jenneker and York. Now in the photodissociation regions, in the massive stars, okay, where they are dissociating all the molecules and so on. Massive star is here, ultraviolet radiation is coming, so you have a H2 region, beyond which you have a H1 region, the atomic hydrogen, and then we have molecular hydrogen region, atomic carbon monoxide region, and molecules further down there. Now the visual extinction from this region to this region out there is about 1 to 10 magnitudes in the visual. Okay, so it's very thick. So you don't see the radiation in the visible light because of this extinction. Extinction actually can be much larger, as I have said, 100 to 200 in the visible region. So even in the infrared, it becomes very difficult. Now this is an embedded massive star in a dense molecular cloud. You can see here, this is the massive star. Ultraviolet energy is coming here. It is destroying all the molecules. This is the ice sublimation. So temperature is now decreasing. Dust temperature is 100 degrees Kelvin here, 90, 50, and 20, so on. So the dust is now destroyed, and their constituent molecules are released in these regions. That's what is the massive protostar is doing here. So you find a number of such molecules here. So polarizes, that means you have an electric dipole moment for these molecules. But if you have a O2 or N2 or such a homonucleus molecules, they don't have the magnetic moment, electric dipole moment. Therefore, they are called apolar ices. So you have polarizes, apolarizes, and so on. So a lot of things are happening. A lot of chemistry is happening outside the star in the embedded dense molecular cloud. Now these are the infrared spectra, because the shocks, I have said, shocks are exciting these regions, and they produce a lot of emission spectrum. This is from 5 micrometer to about 34 micrometer. As I said, these are visibly very difficult regions. A lot of radiation is extinction is there. So infrared only is possible. Infrared and longer wavelengths is possible to find out these. So you can find out lines from hydrogen, helium, carbon, iron, molecular hydrogen, carbon monoxide, water ice, and polycyclic aromatic hydrocarbons. All these signatures are seen here. I'm not going into all the details here. Already time is now running out. But these are PAH emissions here. So this is a PAH emission here. Okay, at 6 micrometer. And then 7 and 8 micrometer, and then 11 micrometer, and so on. And there are other lines. Molecular hydrogen also is there, the rotational lines. Now in the massive protostars, HyperCompact, this is a discovery actually. Some years back they have discovered that there are HyperCompact and ultra compact, because we have seen here classical H2 regions are a few parsec extent, that you have a massive young star, and then around that, because of the ultraviolet flux coming from this massive star, it is ionizing the hydrogen. So these H2 regions, which I have shown some examples like in Orion or M8 and so on, they are parsec sizes. But they have found that at around the similar distances, there are hypercompact and ultra-compact H2 regions. These are much less than 1 parsec, 0.01, 0.1 parsec, and so on. Now, we believe that these hypercompact and ultra-compact H2 regions actually represent these ionized disks that I was actually in the model that I was talking about. So these are the H2 regions that you are talking about when you have observed these hyper and ultra compact H2 regions. So these are the signatures of a protostellar, massive protostellar object. These HC2 and UCH2. Okay. Now there are of course compact and classical H2 regions which are also there, but they show much evolved stars. But if you want to catch these stars in the act, these are the best observations. They're still going on. A lot more observations are being made using the proposed large telescopes in Europe by the Europeans and the Americans. And there are also progenitors of the massive stars in the cloud phase, when you have molecular cloud phase, because we need matter to form these massive stars. We have said about 10,000 solar mass cloud has to be there. So recently they have discovered in the galactic molecular ring, which I have shown a few days back, the galactocentric distance, and this is surface density. And if you see the molecular hydrogen profile here, so this is the molecular ring around the galaxy, like that. So this is the region where they have found out such infrared dark clouds, quite massive infrared dark clouds. This could be the progenitors of massive star formation. Okay. Also, in 1955, I think the maser in the laboratory has been discovered, before actually laser, microwave amplification by stimulated emission. Okay, for which the Nobel Prize was won. But within about 10 years or so, such masers were discovered in the astrophysical context. 1969 or so, the first maser was discovered in the astrophysical context. Now, quickly going through, there are several molecules, methanol, OH, H2O, silicon oxide, and so on, which can be excited, which can be pumped for mazing action. But why these are important for the massive protostars is that they are very, very intense. Therefore, even if they are embedded, even if there is extinction, even if they are very far off, they can be very easily picked up by observations in the millimeter region. So in the microwave region, there are several observations made on this, especially the methanol and OH masers, which require actually a pumping action from the far infrared wavelengths. You need a pumping source, very intense pumping source, which of course the protostar can offer. They can actually stimulate the vibration rotation levels of these molecules. So here there is the upper level A, lower level B. In the thermal equilibrium situation, Boltzmann equation will tell you that these are highly populated than this at a given temperature. So the population over here is less than this one. Okay, but population inversion can be done by pumping up this level preferentially by another source, such as this here, and then you have population inversion. This mechanism is not a thermal equilibrium mechanism, non-equilibrium mechanism, and then they cascade down to give you the maser emission, very intense maser emission. Now there are two ways of doing this one. Several molecules, as I have said, have been discovered in this doing this maser action. So one is to have a radiative masing action where the densities are not high. So such as methanol and OH are stimulated by the intense radiative source nearby the protostar. Whereas the H2O maser, it can be caused by collisions. So you can collisionally excite this level here because the densities are high, but the H2O maser. So H2O masers can be seen even in the low mass stars, but not methanol and OH. Therefore, you look for methanol and OH masers, then you have your massive protostars observed. Okay. Now some examples I'll show here. Maser emission in the ultra compact H2 region, W49 is a very famous cloud. And the OH maser emission, which requires, as I said, low density, but it is a radiative pumping. So all these triangles are all OH masers, and H2O, which is collisionally pumped, they're all here in the higher density regions. Okay, mostly they are present here. This is a high mass star forming region, F49N north. This is a low mass star again, just to show that low mass star also gives you maser action. So this is one jet here, this is another jet here. Okay, this is going this way, this is going this way. Okay, and here in the central region, around the protostar, low mass protostar, shocks are there. So shocks can excite these. Okay, so these are the maser emission, 1.35 centimeter dots here. Okay, other lines are also there, but that's not important. What I wanted to show you that the low mass stars also can show you this, but the only difference is go for molecules like methanol and OH, which require radiative pumping, not the collisional pumping. Now, I have said this already that the multiplicity, massive stars do have normally, I mean, many cases are there that they have multiple systems. They are multiple systems. Orion trapezium cluster they have studied, astronomers have studied, and they have found out that almost nearly a large number of massive stars they do have companions. Okay, you take the Orion trapezium stars here, A, B, so theta 1A, theta 1B, theta 1C, theta 1D. Okay, these are all O type stars, very massive stars. So the theta 1B here has 4 companions in the very high spatial resolving observations. Very high, because these are very less than an arc second. So you need very high spatial resolution for that. Some of it maybe we'll talk tomorrow, but there are 4 components here. There are 2 components here for this star, A star, and for C there are 2 here. Not very much resolved, but there are 2. You please see here, this is 0.05 arc seconds here, this much distance. This is 0.1 arc second here, 0.5 arc second here. But the theta 1D doesn't seem to have a multiplicity. Now, what is its implication? Implication is in the initial mass function. When you have formulated the initial mass function for high mass stars, especially when you go to very high mass stars, above about 10 solar mass or so, we need to take the multiplicity into account in order to put into this kind of a function, which is not done. So that is another issue as far as the massive protostars are concerned. So here I'll stop here and I'll take if there are any questions. Thank you very much for your attention.